Okay, so good morning to all. This is our 11th session of the course Fluid Mechanics. So, in the yesterday's lecture, we started some discussion on the fluid statics, and I gave you one hint at the end that now our task is to determine the forces which are acting on the submerged bodies. Okay, so let's try to see what are the forces acting on submerged bodies. Okay, so we will initially first consider the case of the planar bodies and then we will talk about the curved bodies. Okay, so let's consider that we have some planar object. So say it is of any arbitrary shape, okay, and it is having certain area A, and of course it will be having certain thickness, but that thickness is say uniform throughout. Okay, so this thickness is uniform throughout and this is a planar object. So it can be of any arbitrary shape, but it is actually planar, it is not curved. Okay, so now if this surface is submerged inside a free surface of the water, say so I have water over here or any other liquid or fluid of density rho. So this surface is submerged inside. Okay, so if I take any control surface of area dA over this, I'll be finding that whatever the uh, volume of the liquid column is above this, so through that particular volume it will be, this area will be experiencing the weight of the liquid above this. Okay, so let's try to analyze this situation. So what I will do for this object here, I have tried to give you the three-dimensional representation. Now I will try to draw it on some orthographic projection plane, and there I will try to see how it looks. So let me see, let me draw over here, say this is our nothing but free surface. Okay, so from this free surface, if I see this particular planar object from the side view, then I will be finding from the side view it as nothing but an strip of constant thickness. Is this one clear? So from the side view, if I look, because this is at certain angle and it is having certain constant thickness, so from the side view, if I look, it will be looking like nothing but a strip of constant thickness. Okay, let's consider that this strip of constant thickness is like, if I extend a parallel plane from this, it is coinciding with the free surface at this particular point. So let's say this is my point O. Okay, let me now fix the coordinate system. So let's consider with reference to point O, if I move in this particular direction, this is nothing but my y direction. Okay, and if I move normal to this is nothing but my z direction. Okay, so this is my yz direction, and now I will be having one more coordinate, that is x coordinate. So let's consider that x coordinate is nothing but normal to the board, normal to the plane of the board. Okay, so normal to that I have nothing but x direction. So now what we have to do, we have to determine the forces acting on this object. Okay, so this is the side view. If I try to look it from the top, so top view of the object will give me this particular face that I will be looking from the top. So I will be having this arbitrary shape, whatever I have drawn over here, that I will be seeing from the top, and this is having surface area A. Fine. And this particular arbitrary shape, whatever I have drawn, this will be nothing but in my which plane? This is y direction, and I am looking now normal to the board. So this particular plane will be a x plane, xy plane. Is this point clear? Because it is oriented at certain angle. So basically this is my x-axis, this is my y-axis, and z-axis is actually, so basically this is z and x is normal to this. Okay, so parallel to this you will be finding that you are having x. Fine. Now let's consider that this plane, when we are extending and it is intersecting with the free surface at point O, so it is making certain angle theta with the free surface. Fine. So up to this point anyone is having any issue? Okay. So now if I see this, then ultimately you will be finding, if I take any arbitrary area dA over here. So say this is the arbitrary area. So for example, any elemental area dA I have taken over here. Okay. So this dA will be subjected to some pressure. Okay. So let's consider that it is subjected to pressure P, and as the pressure force acts normal to the surface, so that's why I am drawing the direction of this pressure as normal to this. Fine. And let's consider that this arbitrary location which I have drawn over here, projection of this area. Okay. So this arbitrary location is at distance y from the origin. So this distance is y. Okay. And vertical height of this from the free surface, let's consider it is h. Anyone is having any issue up to this point? Okay. So if I need to estimate the dF amount of the force which is acting on this, can you tell me how much will be the dF? It will be nothing but pressure times dA. Okay. Now, what will be the value of the pressure? Pressure will be nothing but this is my P naught pressure which is at the free surface, and say h is height, so P will be P naught plus rho g. Fine. Now what we have to do, we have to determine this force on our complete surface. Okay. So when I have to estimate the force on the complete surface, I have to, if I have to find out the net resultant force which is acting, that will be nothing but the integration of dF. Okay. And integration of dF will become integration of P into dA. P already we have written as P naught plus rho g h into dA. Okay. Now one important relation, if you see from the trigonometry, then I can write that h is nothing but equal to y sine theta. Okay, so I can replace h with y sine theta over here. So it will be becoming integral of P naught plus rho g y sine theta into dA. Okay. Is it okay up to this point? Now what we are getting that Fr is nothing but equal to integral of P naught into dA plus integral of rho g y sine theta into dA. So if you clearly see P naught is constant, so ultimately I will be getting P naught into integral of dA. I am doing this surface integral over the area A, so P naught into A, okay, and plus rho g. I am considering that liquid is of constant density, so rho and g is also constant, and as well as if it is oriented at some fixed inclination, so that's why, and it's a planar object, so that's why sine theta will also be constant. Okay, so sine theta also I am taking outside, and within the integration now I have y into d. Okay, so now can you tell me what is integral y dA about axis O? Do you know about first moment of mass? Similar to this, we have nothing but first moment of area. So what I am doing actually, dA is nothing but my small elemental area, okay, and it is at distance y from the origin. So basically, with reference to point O, I am multiplying y with dA. So that is called as nothing but this particular term is called as first moment of area. This is nothing but equivalent to the case of estimation of your center of mass. How do you estimate the center of mass? Elemental mass dm multiplied with the distance from the axis. So you will do the summation and then ultimately you get nothing but the center of mass. So over here also, what is this integral of y dA is nothing but it will give me the center of that particular surface area. Okay, so I can write this equivalent to yc, if yc is nothing but my centroid times area. Is this one clear? So it has analogy with reference to calculation of the center of the mass. Now in place of the mass we are talking about area. So that is the reason I am calling this quantity as first moment of area. Okay, so if I take number of small elemental areas and if I multiply to their distance, that will be giving me finally nothing but yc into A. Fine. So that is the reason that I can replace this integral y dA with yc into A, where yc is nothing but coordinate of the centroid.
So here we have to take the analogy of moment of mass, which we have converted. Just you use instead of mass, you use area.
Area, yes. Okay, so now what will be happening? I can replace, so what is yc over here? Let me specify. So this is the plate. This particular plate is having some surface area A. So what will be the centroid of this planar portion? That will be, say, somewhere over here. So the projection of this point on this side view will give me nothing but value of yc. Is this point clear? Okay, so this planar area will be having some centroid based on this area calculation, and whatever the projection of that point I will be finding in this side view, that will be my value yc from this origin. Okay, so let me represent that, say this is my point yc. So I can say that this particular distance, let me represent it like this, this particular distance from point O is nothing but my yc. Okay, and let us consider that yc point corresponding to this, we have this depth as hc. Okay, so at the centroid, whatever the depth of the centroid is, that we are defining as hc. So once again I can write that hc will be equal to yc into sin theta. Fine. Okay, so let me make this replacement in this particular equation. So if I do so, I will be getting my resultant force as P naught times A plus rho g sin theta times, in place of y dA I will be having yc into A, and ultimately I am getting P naught plus rho g yc sin theta into A. Okay, and now I can replace yc sin theta with hc, so it will be becoming P naught plus rho g hc sin theta into A. Okay, is this one clear? Sorry, hc only. Yeah. Okay, so now if you see, what is this quantity P naught plus, what is this quantity P naught plus rho g hc? It is nothing but pressure at the centroid of this planar surface. So I can simply say that this is the PC, pressure at the centroid of the planar surface. So I can simply write my force Fr as nothing but equal to pressure at the centroid of the planar surface times area. Is this one clear? So this is nothing but pressure at the centroid times area. Okay. Up to this point, is it clear? Now let me tell you one more important aspect. So this is a planar surface, okay, which is submerged at an angle theta. Let me draw it again over here. So this is the side view of the surface, and it is submerged under free surface, and it is at an angle theta. So if I have to draw the pressure profile over this, okay, so if I have to draw the pressure profile over this, it will be looking something like this. So here I will be having some magnitude of the pressure. As I am moving towards the other end, which is at the more deeper locations, their magnitude of the pressure will be more. Okay, so here you will be finding magnitude of pressure, say something like this. So now this will be my profile of the pressure. Fine, this is my pressure profile. Now this is the geometric centroid. This is the geometric centroid. Okay, so value of pressure at the geometric centroid, it will be nothing but equal to, because my pressure profile is linear, So because the pressure profile is linear, so at the centroid, whatever the value of pressure I will be getting, that will be nothing but T average. Is this point clear? I have the linear profile and centroid is nothing but representing the geometric center because it is taken based on the centroid of the planar area. Okay, first moment of area. So that is the reason, as this profile is linear, so whenever I will be calculating the value of pressure at the centroid, it will be coming out to be average pressure. Okay, so in other sense I can write that my resultant force which is acting on the surface, this is nothing but the centroid pressure into area, or in other words I can call it as average pressure into area. Is this point clear? Anyone is having any issue up to this point? Okay, now one important point is, whenever we have the force acting over the, it is like continuously distributed over the entire surface. Okay, but of course this force will be having some unique line of action. Okay, so for example, if you are having the surface, and over this surface if the distribution of the pressure is something like this. Okay, so this force is uniformly distributed. So what I can say that if the net effect I have to consider the net amount of resultant force which is coming because of this distribution, I can say that over the entire body, if I have to represent that complete force with a equivalent point force, I can represent it at the center. Is this point clear? What I am trying to say? So though force is distributed at each and every point of the plane, okay, but if I have to represent its corresponding equivalent force with the help of a single line of action, then I can say for this type of situation that my force will be, my point resultant force line of action is actually at this point. Right? So the meaning is, if because of this force my body will be doing any type of translational or rotational motion, that will be oriented from this point. Is this point clear? So that is the reason we are calling this as nothing but the line of action of the force. Okay. So if I have any symmetric situation, then of course this line of action of the force will be at the center. But if I have some situation something like this, where pressure or say distribution of the force is actually not uniform. Okay, so here it is linearly varying over the length. So in this case, can you tell me where will be the line of action of the force? So line of action of the force will be towards the higher magnitude. Okay, so it will be somewhere over here. Fine. So same is the situation. Now if you see this particular pressure profile, you are finding that this is your geometric centroid, but pressure above the centroid is distributed in such a way so that above the centroid we are having lower values of the pressure, and below the centroid we are having the higher values of the pressure. So because of this fact, what will be happening here, somewhere here we will be having some point where we are having the actually line of action of the force. Okay, so let me consider that the line of action of the force is at this point. I have randomly considered that, say my resultant force Fr is acting at this point. Okay, and let's consider that the distance of this point from the origin is yp. Okay, so what I have done now, whatever this continuously distributed force we are having, we have converted it into a single resultant force, and the resultant force is acting at this location yp. Now how to determine point y? Okay, so for determining point yp, what we will do, I will take the moment because of this resultant force about point O, and then I will equate that to the moment of the distributed force about point O. Is this point clear? Or do I repeat it again? Okay. So what I have said is that this is the resultant force, Because of this resultant force, I will take moment about point O. And then I will also take the moment because of the distributed force, okay, about point O. When I will be equating both these, then I will be getting nothing but the coordinate y. Okay, and both the moments should be equal, because the line of action of the resultant force we are deciding based on the resultant effect of the distributed force. Okay, so that's why both the moments should be equal. Then only we will be accurately able to define the coordinate of its line of action. Is this point clear? So if I take this particular moment, then what I will be getting, Fr into Yp. So if you see, Fr is the normal force, so movement is nothing but normal force multiplied by the distance. So in between distance vector and force there should be 90-degree angle. Okay, so here because pressure, the nature of the pressure force is that it acts normal to the surface, so automatically angle is 90 degrees. So that is the reason Fr into Yp, that will be equal to nothing but, now what is the magnitude of the distributed force? The magnitude of the distributed force is P naught plus rho g y sin theta into dA. Up to this is force only. Okay, now we have to convert it into movement. So at whatever y this force is acting, if we multiply that y, then I will be getting nothing but the movement. So I will do multiply by. Is this one clear? So this operation, nothing but I am taking moment about point O, and this I am doing just to determine the value of Yp. Fine. Okay, so let's further explore this. So what I will be finding, that Fr into Yp is nothing but equal to integral of P naught into Yda plus rho g sin theta into integral of y square dA. Fine. So if you see the first term over here, integral y dA, that will be once again becoming yc into a. What about y square into dA? What about y square into dA? The way we define moment of inertia, in the similar way we can define area moment of inertia. Or I can call this as second moment of area. Okay. So what is y square dA? Is nothing but second moment of area or area moment of inertia. Okay. So now if you see, what I can do, I can write in place of Fr, I can write P naught plus rho g yc sin theta into a into yp. Okay, so this is the value of Fr. Have I written it correctly? That will be equal to P naught times, in place of y, now it is y dA, it is yc into a, and then I am having plus rho g sin theta times y square dA. If you just want to operate the mobile phone, then don't come to class. Rho g sin theta into y square dA. So y square dA what will be? It is nothing but second moment of area. So second moment of area, and this is about which point? This is about point O. Okay, and so I will be calling this as, and moreover, when we are taking this moment, I am not taking about point O, but I am taking about the axis which is normal to y at point O, and that axis is nothing but our axis. Fine, because I am talking about area. So if you see from this top view, what I am having, this is my x-axis and this is my y-axis. So particularly I am taking about this point O. This is my point O. Okay, so whenever I am calculating about this point O, so this will be nothing but moment of area about x-axis. Is this point clear? So that is the reason I will be writing this as nothing but I x x I x, I is the symbol for moment of area. So I x x, but I am calculating it about point O. Is this point clear? Now, whenever if we refer to the tables or standard tables, there I will be finding that for different standard shapes, moment of area are given only in terms of centroid of the body. Okay, an axis which is passing through the centroid. So typically we get the values of this moment of area from the tables which are available in different books, etc. Or you can also calculate it from the geometry. That is a even other part beyond the scope of this course. So whenever you will be calculating that, you will be finding majority of the time about an axis, this is given about the centroid. Okay, but we have to find this about some point O. Okay, so what I am trying to say is that I know the value of Ixx at point C, but I need the value of Ixx at point O. So do you know when you have calculated the mass moment of inertia, at that time there is this theorem of parallel axis? Okay, what does it say? It says mass moment of inertia about any between two parallel axes will be nothing but from, if any known point we are having, that known value plus square of distance multiplied by mass. Okay, so here it will be nothing but square of distance multiplied by A. So what is the distance between these two? This is the O axis, this is centroid, so distance is nothing but YC. Centroid. Okay, so distance is YC. So I can say that from the theorem of parallel axis, Ixx at point O will be nothing but equal to Ixx at point C at the center of the body plus rho g sine theta times, sorry, not rho g sine theta, plus yc square into A. Is this point clear? So now I will replace this quantity over there. So if I do so, I will be getting next that P naught plus rho g yc sine theta into AYP equal to, I will substitute also in this and I will also take common this YC term. Okay, so what I will be getting then? Okay, let me first substitute, then I will take common. So P naught YC into A plus rho g sine theta into Ixx about centroid plus YC square into A. Now from here I will be getting P naught plus rho g yc sine theta AYP equal to P naught. So YC terms I will take common. So it will be becoming P naught, area is also common, plus rho g YC sine theta times AYC. Is this clear? So this first term and multiplier with this term I have actually taken AYC common and added together. Okay, and then I will be having plus rho g sine theta into Ixx at centroid. Fine. So from here, if I now take this A and the joining term to the other side, so I will be finding YP is nothing but equal to yc plus ixxc divided by p naught by rho g sin theta plus yc into a. Is this point clear? So this is how we can calculate the line of action of the resultant force. So if you see, this line of action of the resultant force is nothing but yc plus some quantity. Okay, so it means it is lying in the downside of yc. Is this point clear? So it is lying in the downside of yc. So this particular point where we have defined the total line of action of the resultant force, this particular point is called as center of pressure. Is this point clear? So the point which we have drawn over here, this particular point is nothing but called as the center of pressure. Okay, this is one important nomenclature. So we call this point as center of pressure. Okay, and how to estimate the y coordinate of the center of pressure, that we have actually estimated. Fine. So one important point. So right now what we have done, we have considered that the body is completely submerged inside the water. Okay, but many times this happens when body is submerged inside the water, the other side of the body is actually subjected to the atmospheric pressure. That is open to atmosphere. Okay, so when other side of the body is open to atmosphere, so we will be having subtraction of the force from the other side. So many times we can say, we can consider this P naught equal to 0. If pressure is acting from top side also and bottom is also open to the atmosphere, okay, so top side we have P naught plus some additional pressure because of the depth of the water. Okay, so in many circumstances P naught can be equal to 0. So if P naught is 0, then my yp value will be becoming simply yc plus ixxc divided by yc into a. Is this point clear? Okay. Now, what about this Ixx about centroid? So Ixx about centroid, for many standard shapes, it is already, its values are already given in the tables. Okay. For example, if I draw a rectangular cross section, okay. So this is say my rectangular cross section having one side A and other as B, and these are the axes, say this is x axis and this is y axis. Then Ixx for this body about its centroid is nothing but AB cube by 12. Okay, if you have a circle, then for this circle Ixx about its centroid is pi, say radius of the circle is r, pi r4 divided by 4. Okay, if you have ellipse, okay, if you have ellipse and this particular ellipse is having, say this has x axis, this has y axis, this is A, this is B, then you will be finding that Ixx for this about its centroid is nothing but equal to A into B cube by 4. Sorry, pi A into B cube by 4. Okay. So for standard shapes, you will be finding that.
Here it is plane or
No, it is parallel to the plane. Because if you recall the previous figure, so we are talking about area A and x-axis is nothing but parallel to that area A. Okay. Up to this point, is it clear? Okay. Now, based on this understanding, we can define one concept which is called as pressure prism. Okay. So if I take that I have some object So this is the plate or any object, and it is actually submerged in water. So once it is submerged in water, we will be finding that it is subjected to the pressure force. So of course from the top side pressure is something like this, and from the bottom side magnitude of the pressure will be more. Okay, and if I see the total pressure distribution over this, then it will be forming nothing but a shape of a prism. Okay, so if you see, this is nothing but the pressure distribution over this. So this side I have pressure, and this side, this is nothing but it is representing the area, this plane and this plane. So this is say y, this is x. So multiplication of x and y will represent nothing but the area. So if I say the volume of this particular prism, is nothing but equal to integral p dA. Is this point clear? Because this side is p and multiplication of x and y will form a. So volume of this particular prism is nothing but equal to integral of p into dA, so which is equal to the resultant force. So that's why we call this as nothing but pressure prism, and its volume is equal to the net resultant force which is acting because of the water pressure. Is this point clear? Now whatever the centroid of this prism we will be taking, so this volume will be having some centroid location. So whatever its centroid is there, the projection of that centroid on xy plane is nothing but gives us the value of center of pressure. So what I am having the centroid of this particular volume and projection of this centroid on the plane. So say this is the projection of the centroid on this plane. Okay, it should be somewhere near the bottom. So say it is here. So this particular point is nothing but my center of pressure. And center of pressure is nothing but what it is? Yes, line of action of the resultant force, or in terms of this particular graphical representation, I can say it is the centroid of a projection of centroid of pressure prism. Okay. So once you have this information, you can utilize this to determine the forces acting on different solid surfaces which are submerged in water. For example, you are having the gate of a dam. You have to determine the force. Then only you can define what should be the thickness of this, what should be the material of that particular surface. You have to design a submarine. So what are the forces acting on different surfaces of the submarine? Then only you can do its structural design. Okay. But when we talk about the submarine, now comes complexity. If I consider the dam, most of the times we'll be finding that gates or walls of the dam are nothing but of planar shape. Okay. But if you talk about the surfaces of the submarine, these are nothing but of curved shape. Okay. So these are not planar surfaces. So what happens when our shape of the surface changes from planar to the curve? Okay, so that is our next topic. We have to determine the forces acting on curved surfaces. Okay. So if I take arbitrarily any curved surface which is say submerged in water, of course it can have three-dimensional profile. Okay, so how can we determine the forces? For determining the force on this curved surface, you have to first determine distribution of pressure over this entire surface. Okay, and then you have to take the surface integral of that. But its surface area and things are oriented in different directions. So that's why it will give you the lots of complexity if we go for the geometrical integration. Okay, if we go for the integration of PDA over this entire surface, because it can be of any arbitrary random shape. Okay, so what we do, this is the reason that whenever we consider the curved surface, we go for actually slightly different approach. Okay, and by using that particular approach, we can utilize the knowledge which we have just now developed for the planar surfaces in order to estimate the forces given for curved surfaces. Okay, so how we go with this approach, that let me explain to you. So say this is my free surface, and if I look from the side view, then say curvature of the curved surface is say looking something like this. So this is the solid curved surface which is submerged in water, and from the side view it is looking like this. Okay. Now, of course, it is containing some water over this. So here if you see, this is nothing but the boundary of the water which is present in this reservoir. Okay, so this all is water. Okay. Now out of this boundary, my curved surface is only up to this portion. So any liquid which is present away from the curved surfaces, that is not of my interest. Okay, my interest is with the liquid which is present just close to the curved surface. So what I will do, I will draw a control volume within the periphery of this curved surface. So this is the liquid volume which I have considered. Okay. Now, with this liquid volume, what will be happening? This liquid volume will apply certain amount of resultant force over this curved surface. Okay, and that resultant force over the curved surface. So if I consider this is my boundary of the curved surface, so say resultant force over this curved surface because of the liquid is acting in this direction. Fine. So this force will be having two components. One will be vertical component and one will be horizontal. Okay. Now the way fluid is applying force on the curved surface, from the Newton's third law, this solid surface is also applying the equivalent amount of force on the liquid in order to support that liquid. Okay, and this is just in the opposite direction. So what I can say that if I take this black colored liquid volume, on this black colored liquid volume, there is a force, a resultant force, which is acting in opposite direction due to this solid surface. Is this point clear? And of course this force is also having two components. One is Fh and one is Fv. Okay. So if by doing the equilibrium analysis for this liquid control volume, if I can estimate the value of Fh and Fv, then ultimately nothing but I am calculating the force which is acting on the curved surface. Is this point clear what I am saying now? So if I just estimate the forces which are acting on the control volume of this liquid, okay, if I simply estimate these forces, and then I will be getting the value of Fh and Fv, and then by knowing this I can know the resultant force which this surface is applying on the liquid column. So same force will be applied by liquid column on the surface. So this is the easiest approach. So how this approach is easiest? Because now this is the projection of the surface in vertical plane. So this is nothing but this vertical line is nothing but the projection of curved surface on vertical plane, and this line is projection of curved surface on horizontal plane. Okay. So these two projections are nothing but now forming the planar surfaces. Though surface as a whole it's a curved surface, but its projections on horizontal and vertical planes will be nothing but the planar surfaces. Now we already know how to estimate the forces on the planar surfaces. So by using the similar concept, actually we can determine the values of Fx and Fb. Okay. So how to do this? I will try to explain you in the next lecture. Now we'll stop. If you have any question that you may discuss.